Hello to everybody. Today I want to derive some equations of motion for masses affected by gravity. So, for example, a sun and some planets or whatever. So we will need some static reference frame with whatever number of dimensions we want to consider. I want to draw two of them, x and y. Then we will have one body, which I want to call I, that will be affected by gravity, and we will be interested in the motion of this body. And there will be other bodies. For a start, I just want to consider one of them. I want to call this one body J. And those other bodies will affect the motion of that. Both of those masses will be described by two characteristics. On the one hand, they will each have a mass, mi and mj. And they will both have a position given by vector xi and vector xj. Now that we know this, we can also figure out what the distance between those two planets is, and I want to call a vector pointing from I to j rij vector. This vector can then obviously be found by vector rij is equal to xj minus xi. I want to use Newtonian mechanics to describe the motion of those planets, which means I will use forces to express motion. And the force caused by J on I will be called Fij. And Fij will have a length, will have an absolute value that is equal to some constant times mi mj over rij squared. Why is that so? The mi, mj, of course, are each just the masses of those planets, and it would be weird if that wasn't proportional. Then the dividing by rij squared, so the distance between those two squared, that has to do with the field, the gravitational field spreading out over a greater space. If we take one point from which the gravitational field is sort of coming, and then we take a rectangle or square in a set distance to that, and we take another rectangle in twice the distance, and we just want to trace those, and we want to make the sizes of those rectangles or squares, or technically any shape, such that we can project them in this way. This second farther rectangle will have 4 times the size of the one that is closest to us, just because everything spreads out over a wider area. So that's why we have 1 over r squared in there. And of course it would be way too easy if all of this was just equal, so it's just proportional, and we need some constant in order to actually do this. This constant gamma can be found in an experiment, and it turns out to be about 6.67 times 10 to the 11 cubic meters per kilogram second squared. But of course the absolute value of the force is no good if we want to calculate anything, so we need to write this in vector form, and the direction of this vector Fij is just what I drew here in my next picture. So Fij vector is equal to just what I wrote above, gamma mi mj over rij squared, in the direction of rij hat, which is a unit vector pointing in the direction of rij, just because, as I drew here, the force is supposed to point right at the other planet. Everything else would be weird and would imply that momentum isn't conserved in that system and all of that. So we need that force to point on the other planet. Now, rij hat, the unit vector pointing in the direction of rij, can be written as rij vector over rij absolute value. And of course, rij absolute value is just rij, as I wrote it up here. So that I can rewrite my equation in the form Fij vector is equal to gamma mi mj over rij. Now not squared anymore, because we have another rij up here to add to it. So, no, to multiply it, of course. So we cube this, and we multiply with rij vector. So this is the equation, and if we have a set of point masses which interact gravitationally with each other, we just have to make sure that this relationship holds mutually for all of those point masses. So let's assume we have n masses. They have masses m1 through mm and positions x1 vector through xn vector. In this case, we can consider this just as a sum. The force on the ith body, which is one of those n bodies here, so the total force, Fi total, is just the sum of all the masses as they interact with our mass I. So Fij is the force that that body j acts on body I, and if we just add up all of them, we get it. But I want to understand I such that it is between 1 and n, and that the ith body is actually in that set, because that will be easier to program in a later program, and we will soon see that a computer will be needed to solve this. So I have to make sure that we don't consider the interaction of I on itself, so j must not be equal to I. Okay, a very well-known concept in physics, the Newtonian law, is that force is always equal to the mass of whatever it's acting on times the acceleration of it, and that works with vectors. And acceleration is just a second derivative with respect to time of the position of whatever our force is acting on. So that's mx vector dot dot. We can now use this knowledge and write this as mi, the mass of whatever that force is acting on, times xi vector dot dot, second derivative, so acceleration. And that's equal to our sum of j equal to 1, where j is unequal to I. And now I want to write Fij with our equation from above. So that's going to be gamma mi mj over rij cubed rij vector. Notice that we have an mi here and an mi here, so we can just cross out those two, and we end up with our final result. That is that the acceleration of our ith particle is equal to gamma times the sum of j equal to 1 till n from j unequal, where j is unequal to I, over mj over rij to the third power rij vector. Oh, and of course I forgot the n up here. So this is an equation of motion. It's a ordinary differential equation of second order, because we have the second derivative in here, and hidden in the rij we also got the current position, so this makes it a second order case. And unless you make some major simplifications, like maybe you only consider two bodies, so n is equal to 2, but unless you do that, you won't be able to solve this symbolically, and it will take a computer to approximate a solution for this. Thank you for watching.